Okay, so uh, I actually had recorded a lot of this yesterday, and then I ran into um, issues. Well, like there were two things. First, I had like recording issues again, but it was not sound this time. It was just more like I selected too high of a quality to record in, and I thought that I would be fine because I have like this eGPU now connected to my mini PC, which handles my streaming. But I guess I still need. I still have a lot to learn about how to record things. I mean, it's obvious, right? Like I always have these like issues once in a while, but yeah, I had this. I had selected like NVENC to record, and then I also like I was like, oh, okay, since I'm using something that relates with NVIDIA, and I'm also on a NVIDIA eGPU, I might as well choose the best thing and then up the quality. But turns out like that put way too much load on the GPU itself, and OBS stopped recording like halfway through. But that's okay because as I was like trying to work out and preview, we're gonna do a lot of fun stuff today, coding wise. As I was trying to code up this next section of the book, which is basically creating our own system call in the Linux kernel, I was having really like bad issues with like trying to figure out how to actually place the code in specific files because the book is actually not that clear on what to do, and I had to like poke around to understand what exactly to do, and so um, preview whatever the book says is like it's accurate, but I think it's not exactly the best way to do it, or not best, but it's not the easiest way to do it. So I'm gonna like take a little bit of like a tangent and do it a different way, but I think that way will be more clear and straightforward. So I think it's just worth just redoing this video anyway. So I'll just start from where I left off, and then we'll go from there. Okay, and then as I'm doing that, I'm like monitoring the my task manager on my streaming PC, just to, or not streaming, my recording PC, just so that I don't overload the system again. I can see like the integrated GPU is already at like 71%, and the RTX 3060 is already at 85%. So it's kind of pushing it. So anyway, uh, okay. So system call context. So as discussed in chapter 3, the kernel is in the process context during the execution of a system call. So meaning that whenever the kernel is actually executing some sort of system call, it's still kind of executing within the context of the process, meaning that it's executing this system call on behalf of that process. So the current pointer points to the current task. So remember, we always have this special current variable, pretty much, that always tells us exactly which is the active task in user space. Because if we're in kernel space, sometimes we want to access or we want to answer specific questions, just as like, what is the current task running in user space right now? Who am I actually executing this system call for? This is where the current pointer actually references back to. And that, again, is the process that issued the system call. So in process context, the kernel is capable of sleeping. So for example, if the system call blocks on a call or explicitly calls schedule, and it is fully preemptible, these 2 points are important. First, the capability to sleep means that system calls can make use of the majority of the kernel's functionality. As we will see in Chapter 7, Interrupts and Interrupt Handlers, the capability to sleep greatly simplifies kernel programming. Cool. Answer message. Okay. So the fact that process context is preemptible implies that, like user space, the current task may be preempted by another task. Because the new task may then execute the same system call, care must be exercised to ensure that system calls are reentrant. Okay, so let's actually digest what that means. Okay, so let's remember that the kernel has like the over, like it knows everything, right? It knows all the memory. It doesn't virtualize that. It knows how to access the file system directly, and it has access to like all the CPU registers. Okay, so there's something funky around this whole idea, is that when the kernel, right, is executing something for a process, and something preempts, right, meaning that an active process is now kind of put back into the ready queue, and then a new process comes into to run. The kernel has to actually switch its mindset from handling the previous process and handle this new process that just came in. Now, since the kernel is preemptible, that means during some system call, for example, if preemption occurs during that system call for that old process, if a new process is now running, and it also is working on that, like let's say it calls the same system call as a previous process for whatever reason, the kernel kind of has to be able to take care in knowing the difference, right, between like whose system call is this really for, because again, like reentrancy means that you can be like pulled away from whatever you've been doing at any moment and then put back, and you're supposed to actually still maintain like the correct state. So yeah, I think this is probably a confusing part of kernel programming, like the whole synchronization aspect of it. I think for now, like the way I'm understanding is that just know that that is possible and that we had to do something, but I wouldn't stress about it right now. So until we know more or want to do more. So of course, this is the same concern that symmetrical multiprocessing introduces. Synchronizing reentrancy is covered in Chapter 9, An Introduction to Kernel Synchronization, and Chapter 10, Kernel Synchronization Methods. So when the system call returns, control continues in system call. This is the function, right? Which ultimately switches to user space and continues execution of the user process. So the final steps in binding a system call. Oh shit. Let's see. Final steps. Right there. Okay. Okay. So final steps in binding a system call. So after you have written a system call, so after the system call is written, it is trivial to register it as a official system call. So first, we need to add an entry to the end of the system call table. So remember, all system calls are ID'd in some sort of array. This needs to be done for each architecture that supports the system call, which for most calls is for all architectures. So if you want to introduce a new system call, it's best to try and implement and introduce it to all architectures available. So if you're like writing a new system call, writing it for like ARM, x86, x86 64, I don't know, back then I guess Spark was still in concern, PowerPC, things like that. The position of the system call in the table starting at 0 is its system call number. For example, the 10th entry in the list is assigned system call number 9. So system calls start at 0, so there's 0 index. So we have 100 of them, then the last one would be ID 99. So for each supported architecture, define the syscall number in asm uni.std.h. Then we need to compile the syscall into the kernel image as opposed to compiling as a module. This can be as simple as putting the system call in a relevant file in kernel / such as sysc, which is home to miscellaneous system calls. Okay? When we say compile the syscall into the kernel image, we mean actually to implement it in kernel code. It cannot be loaded as a module, meaning that when we implement a system call, we have to just put it inside the kernel, like the file, or maybe make the modifications in the file that would get compiled into the kernel. So that's what it means. System calls have to be like tightly coupled with that kernel. So okay, so now they're gonna show us like how to create a system call. Look at these steps in more detail with a fictional system call called foo. First, we want to add sysfoo to the system call table. For most architectures, the table is located in entry S and looks like this. So yeah, basically every system call gets like an ID in this order. So comment here, right? 0, and then all the way down to 335, 36, 37, 38. So 338. Sysfoo is a system call for our foo, our pretend system call foo, right? And that's 338. So the new system call is then appended to the tail of this list, long sysfoo. Although it is not explicitly specified, the system call is then given the next subsequent system call number, in this case 338. For each architecture you want to support, the system call must be added to the architecture system call table. The system call does not need to receive the same syscall number under each architecture. So that's important detail. Although it's like 338 here, this is, let's say this is for x86, right? If we were trying to implement the same system call in x86 64, that would actually be it could possibly be a different number. And then like ARM would also have a different system call number too for sysfoo. So they don't necessarily have to be the same from architecture to architecture. So just one thing to be aware of. Yeah, so it's a system call number as part of the architecture's unique ABI. So usually you want to make the system call available to each architecture. So again, we would, if we're going to introduce a new system call, we kind of want to implement it for all architectures. Note the convention of placing the number in a comment every 5 entries. This makes it easy to find out which system call is assigned to which number. Next, the system call number is added to asm.uni.std.h, which currently looks somewhat like this. So then after we have defined this number up here, we then add the system call into the asm.uni.std.h. And again, it's more or less like the same, just adding it at the end of the list like this. Define nr foo 338. So it'll be thunder nr underscore and then the name of your system call. I think that would be sort of like the same name you would use when you want to call like a C function, for example. Okay. So, and we'll walk through all this together, but not in these exact steps, I guess. So finally, the actual foo system call is implemented because the system call must be compiled into the core kernel image. So that's what it means to compile into compile the kernel image with the system call. So it means that we have to modify the kernel code to include it and not load it as a module. Okay. So in this example, we define it in kernel sysc. You should put it wherever the function is most relevant. So for example, if the function is related to scheduling, you could define it in kernel/schedc. So this is how it's done here. This is how you implement sysfoo in this case. So that we've defined it to exist, or we declared it to exist. Now we need to define it. We need to implement that so that user space code can call the new system call, and this would actually be the code that runs in kernel mode for that. Okay, so then that's it. Boot the kernel and user space can invoke the foo system call. But then we have a problem, right? Like, how do we actually write a user space program that actually can tap into the system call? Because obviously, user space programs are written in regular C, so using the C library. But the C library isn't really aware of your system call, right? It's just new, right? You didn't like also push a PR to the C standard library to now be aware of your system call or anything. So how would you use that right away? So you would do something like this. So accessing the system call from user space. So generally, the C library provides support for system calls. User applications can pull in function prototypes from the standard headers and link with the C library to use your system call, or the library routine that in turn uses your syscalls call. If you just wrote the system call, however, it is doubtful that glibc already supports it. So thankfully, Linux provides a set of macros for wrapping access to system calls. It sets up the register contents and issues the trap instructions. So remember, there was like a whole setup involved with system calls, like with setting your registers to specific values. So there's actually a macro in the C library that allows this to happen in the background. And that's all that's needed, really. Like, that's the important part, is to actually execute a syscall trap, right, in assembly, and then after that have it peek into what number the system call to execute, and then based off of that number, we look into the stack for the arguments, and then actually just run that piece of code there. It's not going to be pretty. It won't be like just simply calling the function, but we'll actually have access to it, and we'll see this example. So these macros are named syscall n. So syscall 0, 1, 2, 3, 4, 5, 6, where n is between 0 and 6. So that signifies the amount of arguments to expect. The number corresponds to the number of parameters passed into the syscall, because the macro needs to know how many parameters to expect and consequently push into registers. So for example, consider the system call open. Okay, open, a real existing system call, defined as long open const char file name int flags int mode. So this is like the signature, the declaration for our open system call currently in the kernel. We didn't write this, it comes with it, right? So the syscall macro to use the system call without explicit library support would be something like this. So say we introduced this open, and the C standard library still hasn't really included a real header to this, right? This open system call. Well, if we didn't have that information, we can recreate that call by doing this in C. So having underscore syscall 3, first defining the open the open system call ID, which was 5. If we look back into that unistd.h in ASM for the kernel code, we would have found that it's 5. So we just define it here again, and then we use this syscall 3 macro, and what we put in to this list of arguments would be like the return type, right? The name of the system call, and then the type of the first argument, the name of the first argument, the type of the second argument, the name of the second argument, the type of the third argument, and then the name of the third argument, and then so on. That's the pattern how we actually do this. So then the application can then just simply call open, because we define the name to be open up here. Now, for each macro, there are 2 plus 2 times n parameters. So in this case, n would be 3 here. So there should be, 2 times 3, which is 6, plus 2 is 8. So it's 1, 2, 3, 4, 5, 6, 7, 8 parameters for this type of syscall, because there's 3, and there's 3 in this case. So the first parameter corresponds to the return type of the syscall. The second is the name of the syscall. Next follows the type and name for each parameter in order of the syscall. System call. The nr open defined is in asm unistd.h. It is the system call number, and the syscall 3 macro expands into a C function with inline assembly. The assembly performs the steps discussed in the previous section to push the system call number and parameters into the correct registers and issue the software interrupt to trap into the kernel. So again, that's what this macro does. These syscall n macros basically executes all the system call, like the entrance to the system call manually by setting up all those registers, like putting that specific value into EAX, and then invoking that trap so that it can be read in, and that value in EAX, I believe, will then lead us to telling the CPU to execute the system call, but then what system call, and that's another value and so forth. And that value is going to be the one that we would implement. Okay, so now this is the user space program. So placing this macro in an application is all that is required to use the open system call. So let's write the macro to use our splendid new foo system call and then write some test code to show off our efforts. So here is basically the user space program. Okay, so that's how you would use it. So in this case, foo took no arguments, so we did syscall 0. But then we do that 2 plus 2 times n thing. So 2 times n is 0 plus 2. That's why there's going to be 2 arguments here. Okay, just the return type and then the name of the system call so that you can just use it like this in C. Okay. All right, so let's actually try this out. Like, let's create our own system call inside the Linux kernel and then try it out. So what's first, right? So like the first thing he said is, or the author says, is to actually add the ID to some sort of table. In this case, all we need to do is add it into asm.unistd.h for our specific architecture. Our specific architecture is going to be x86-64. So we had to find that corresponding unistd.h inside. So it'll be like x86/asm/ or sorry, x86-64/asm/unistd something, right? It won't be exactly like that, but something similar, the corresponding version to it. So if I open up Vim right now, and then if I were to search for a file called unistd.h, I would actually find that there's a lot of these types, right? So you have Motorola 68K right here. So this is like M68K. You also find x86, and then here you see how x86 in this file preview here. It leads us to 2 paths, right? If we have a 32-bit, we'll go to unistd_32.h. Otherwise, we go to unistd64.h. So I think for us, we're going to do unistd64.h because that's what our virtual machine is on. And so we'll pick this one right here. So we're now in asm unistd_64.h. And it's actually, okay, so this is the reason why I said it was like different, right? This is actually different from what the book says, because the book has it simple like this. But apparently for 64-bit, or at least x86 64-bit, it's different. It's just slightly different, but we can actually kind of understand exactly like what's kind of going on here. It's not that big of a deal. It's just slightly different, but we can just like emulate it by just following the same examples. So we just like kind of just scroll down all the way down. Like, let me just do this. We'll find the last system call. Oh, I didn't even. I know why. I didn't reset my stuff. Okay, get reset. I don't want to spoil it. So I'm gonna go back, and then I'm gonna do. How do I do this? Git checkout. Do I do git checkout origin? Arch x86. Let me just reset what I've done. I'm spoiling it all. I want to do this live, you know. Okay, do I have it still? Let's see. Yeah, it takes a while because it's still over in NFS, but I'm gonna check out everything else. So that works. Include Linux syscalls.h, and then we also have kernel sys.c. So we only need these 2 files. And then ready to get status again. We should be ready for real implementation. You didn't see anything earlier. Okay, so yeah, that's just our kernel image. Okay, so we were to go back again and go to unistd_64.h with the x86 one, and then we go all the way down and go back up just a little bit. We'll see that the last system call to be defined is 299. Okay, now why is that not like the book where it's 338? As it turns out, the book is actually going with 32-bit x86, and 32-bit x86 has a lot more legacy type system calls, whereas in the 64-bit version, there's less system calls implemented, mainly because it just doesn't support some of the 32-bit ones. So no worries on that. We only care about implementing our system call for x86 64 today, because even though like the book says you should probably do it for every single architecture, we don't have time for that, and we don't really have like a way to really test that. So let's just focus on 64-bit today. So I can just do this nr, right, and we'll call it sum num, because that's what we want. We want to create a system call right now to sum up two numbers. Given an a and a b, we want to return back a plus b. We'll just call this system call sum num. So your system call is going to be prefixed by dunder nr underscore, and then we'll just do sum num like this, and we have to give it a number, and that'll be 300 in this case. And we just use this system call macro and just do the same thing. It's kind of straightforward. And then just kind of say, okay, now I want this to be called sys what? Sum num. And you just gotta be consistent. Okay. So that's gonna be our definition in UniSTD64.h. But we also need to kind of declare all this in syscalls.h. Right, so syscalls.h. I think that will be in probably x86-64. Okay, so this one is going to be, in this case, the function declarations, right? The function declarations, I think it's our function declarations. Is it this one? Let's see. No, this is sysfork. Let's see what we had. Including syscalls.h. Yeah, that was right. Syscalls.h. Yeah. Okay. Yeah, syscalls.h. Sorry. Include Linux syscalls.h. Okay, so like notice here as we scroll down, we see a bunch of syscalls like that looks like this, right? So here is actually where we will actually define the function declaration for our syscall. And you know, we have a bunch of existing ones here already with the ASM linkage, and that actually goes back to what the book was saying here. This ASM linkage here, this ASM linkage, I guess decorator, this label, along with the return type, the name of the function, and its parameters, right? And so if we were to go back here, all we have to do is just tack that at the end of this file here, and then have sum num exist. So as a linkage long, it will return a long. That's what our system call is going to return. It's just going to take two numbers again, two integers, and just give back a long. So we'll do asm linkage long sys underscore sum num, and that was the same name that we defined in unistd underscore 64.h. And then we'll give it two arguments, which is going to be int a, int b, and then that's it. That's our declaration here. So now we need to actually implement this thing, right? So we have our declaration. We want to actually implement it in code so that we can access it. How we do that now is find a file where this syscalls might be included somewhere. And the book had already mentioned we just got to put it in kernel, right? And I'm just going to put it under sys.c. There's no reason why. I just found that it was just convenient. So I'm going to put it under kernel sys.c here. And I just found a spot to do it. And the reason why I decided kernel sys.c is because actually this file syscalls.h that we included earlier was there. So yeah, just find a spot really. Because we don't really depend on anything else. So I'm just going to put it right before this one here. So I'm just going to comment this to be our system call sum num. And then we had declared it to be asm linkage long, I think it was sys sum num. And then we had int a, int b, okay? And then in this case here, we want to, let's just do print k. So print kernel, kern info. Then we can say average dev sys sum num receive two args, and we can just say, we can just log what arguments we receive, a and b, and then we'll just return a plus b. Okay. We can actually just ignore this as a linkage thing. I think it will get included when you compile the kernel, so that's fine. This looks scary, but yeah, just trust it. Just trust the system. Okay, so now we have those three files, in this case, all ready to go. And what's next is, so we've defined like that we have a new system call called 300 sum num. We've declared it in our kernel function for it, and then we've implemented that function. So now all we need to do is just compile the kernel to include our new system call, and then reboot, and then see if it's available by writing a program, a regular C program, to make use of it. So again, just three files. If I were to go here and did git diff, okay. Okay, so then here we go. We have UniSCD 64 here. We did our change by adding syssumnum 300. And then we just declared some function somewhere that we can access. And then we just implemented that. I think that's all there is to it. And then now we can go back to our VM. And then we can just make J24. And then see what happens. Okay. So going into here, we can do make J24, and that's actually going to take some time. Way more time than I would like. I think something triggers the kernel to like not do an incremental compile, but like compile a lot more files. We just take a look at system monitor here. Yeah, it's going as quick as it can. Okay, so as we're doing that, let's read more here. Okay, so, and we'll write our user space program after the test. Okay, so accessing the system call from user space. So wait, I just did this. Well, hey, why not to implement a system call? The previous sections have shown that it is easy to implement a new system call, but that in no way should encourage you to do so. Indeed, you should exercise caution and restraint in adding new sys calls. Often, much more viable alternatives to providing a new system call are available. Let's look at the pros, cons, and alternatives. So the pros of implementing a new interface as a syscall are as follows. First, system calls are simple to implement and easy to use. Second, system call performance on Linux is fast. So these are the benefits of implementing a system call. Okay, now the cons. You need a system call number, which needs to be officially assigned to you, and that's different for every architecture. After the new system call is in the stable series kernel, it is written in stone. The interface cannot change without breaking user space applications. Okay, it's a huge responsibility. Each architecture needs to separately register the system call and support it. And system calls are not easily used from scripts and cannot be accessed directly from the file system. Because you need an assigned system call number, it is hard to maintain and use a system call outside of the master kernel tree. So for simple exchanges of information, a system call is overkill. And that's what we just did. We just basically did a simple calculation. So what are the alternatives? Well, if you're just going to pass information around, you can just implement a device node and read and write to it. I think this is basically a virtual device driver for it. Use IOCTL to manipulate specific settings or retrieve information. So that's like the catch-all IO system call. Certain interfaces such as semaphores can be represented as file descriptors and manipulated as such. Add the information as a file to the appropriate location in sysfs. Okay, so for many interfaces, system calls are the correct answer. Actually, they are the correct answer. Linux, however, has tried to avoid simply adding a system call to support each new abstraction that comes along. The result has been an incredibly clean system call layer with few regrets or deprecations. Interfaces no longer user supported. The slow rate of addition of new system calls is a sign that Linux is relatively stable and a feature-complete operating system. Conclusion. In this chapter, we discussed what system calls are and how they relate to library calls and the application programming interface, or API. We then looked at how the Linux kernel implements system calls and the chain of events required to execute a system call, trapping into the kernel and transmitting the system call number and any arguments executing the correct system call function, and returning to user space with the syscall's return value. We then went over how to add system calls and provided a simple example of using a new system call from user space. The whole process was quite easy. As the simplicity of adding a new system call demonstrates, the work is all in the syscall's implementation. The rest of this book discusses concepts and kernel interfaces needed to write a well-behaved, optimal, and safe system calls. Finally, we wrapped up the chapter with the discussion on the pros and cons of implementing system calls and a brief list of the alternatives to adding new ones. And that is chapter 5. We're going to go to kernel data structures, but this is going to be a big one because we had to learn linked lists, queues, maps, and binary trees. And they're not like the traditional way of doing it, so let's actually now focus our attention to just our system call stuff. Okay, so we're still compiling, but I just want to show you the user space program that I have already. Okay, so here it is. So this is actually a regular C library that can C program that can compile. Notice here that I have it different from the book. So I included some two important headers here, and all I did was I declared or defined a macro that leads us back to our system call where it's like 300. Really, it's just a variable. I could have just put 300 here. There's a special, there's a special function we can use in syscall.h that allows us to just execute any system call given its ID and then passing in the arguments. Okay, so that's what we just did. We just did it the manual way here. There's no such thing as a sum num system call yet in the C standard library, at least for this version. We just created it, but we want to access it directly by the long way of doing things. And I think this is a great mechanism. So then we just do this, execute our system call, get back a result, and then we'll just log it. And then we had print something out in the kernel, so we'll go to dmessage and look at the kernel printing for that. Yeah, so I think we just need to wait a little. From what I remember, it is long, but it's not like from the beginning long. I should probably not compile these drivers anymore, these tuner drivers. Okay. Maybe it is take a good opportunity to look at some of these logs and see what I need or don't need. Just try to accelerate that compile time even more. DVB, I don't know what these are. Okay, so what do we do? Okay, so as we're waiting, let's just get a preview for kernel data structures. Why not, right? It looks like we're not going to error out here. Yeah. Okay. So kernel data structures. This chapter introduces several built-in data structures for use in Linux kernel code. As with any large software project, the Linux kernel provides these generic data structures and primitives to encourage code reuse. So the Linux kernel has built-in data structures that can be reused. Kernel developers should use these data structures whenever possible and not roll your own solutions. So don't re-implement a simple data structure. In the following sections, we cover the most useful of these generic data structures, which are the following. We cover linked lists, queues, maps, and binary trees. We conclude the chapter with a discussion on algorithmic complexity, the ease with which algorithms and data structures scale to support ever larger inputs. Okay, I think this is like going to be a fun one for all the computer science people. I'm going to struggle a little bit because I don't, I know how to implement these in other languages, but not in C. So we'll probably just do a lot of examples together. Okay, so first we have linked lists. The linked list is the simplest and most common data structure in the Linux kernel. A linked list is a data structure that allows the storage and manipulation of a variable number of elements, called nodes in the list. Unlike in a static array, the elements in the linked list are dynamically created and inserted to the list. Okay, so far so good. That's like a normal linked list. Okay. We can just continually add new nodes to the list, ever growing, not worrying about some sort of fixed capacity like an array. Okay, so this enables the management of a varying number of elements unknown at compile time. Because the elements are created at different times, they do not necessarily occupy contiguous regions in memory, so they can be all over the place given that they're linked. Pointers to other pointers. So therefore, the elements need to be linked together, thus each element in the list contains a pointer to the next element. As elements are added to or removed from the list, the pointer of the next node is simply adjusted. Okay, so that's a linked list. Okay, still going. Okay, singly and doubly linked list. The simplest data structure representing such a linked list might look similar to the following: struct list element, then we have the data that is inside that node, and then we have a pointer to the next node, list element, list element. This is what we call that recursive data structure, right? This is a linked list that we know and love. So looks like this. Okay, again, the linked list that we know and love, because it's going to be really different in Linux. In some linked lists, each element also contains a pointer to the previous element. These lists are called doubly linked lists because they are linked both forward and backward. Linked lists, such as the list in figure 6.1, do not have a pointer to the previous element. That do not have a pointer to the previous element are called singly linked lists. Okay? So we only have one pointer to the next element. That's a singly linked list. A data structure representing a doubly linked list would look similar to this. So basically the same element, except now we have a previous pointer. Okay. Oh, jeez. Okay. Gotta really fix this drivers thing. They're all modules too. Okay. Moving on. So yeah, you'll notice that there's like a pointer called previous that points just to the previous node directly. Straightforward. Okay, now circular linked lists. Normally, the last element in a linked list has no next element. Okay, it points to null. It is set to point to a special value such as null to indicate that it is the last element in the list. In some linked lists, the last element does not point to a special value. Instead, it points back to the first value. This linked list is called a circular linked list because the list is cyclic. Circular linked lists can come in both doubly and singly linked version. In a circular doubly linked list, the first node's previous pointer points at the last node. Figures 6.3 and 6.4 are singly and doubly circular linked lists respectively. So the last node points back to the first node, so it's just on and on and on. And then it could be even more confusing with previous. The head previous points to the tail. Okay? Although the Linux kernel's linked list implementation is unique, it is fundamentally a circular doubly linked list. Using this type of linked list provides the greatest flexibility. Of course, because you have pointers everywhere. Pointers to any other node that you want to access. Okay. Alrighty. I think I want to. Let's keep going. Okay. So moving through a linked list. Movement through a linked list occurs linearly. You visit one element, follow the next pointer, and visit the next element. Again, the linked list we know and love. Rinse and repeat. This is the easiest method of moving through a linked list, and the one for which linked lists are best suited. Linked lists are ill-suited for use cases where random access is an important operation. Instead, you use linked lists when iterating over the whole list is important and dynamic addition and removal of elements is required. In linked list implementations, the first element is often represented by a special pointer called the head. This enables easy access to the start of the list. And remember, the head can be at any point. It's up to you. It's in your relative view. In a non-circular linked list, the last element is delineated by its next pointer being null. In a circular linked list, the last element is delineated because it points to the head element. Traversing the list, therefore, occurs linearly through each element from the first to the last. In a doubly linked list, movement can also occur backward, linearly from the last element to the first. Of course, given a specific element in the list, you can iterate backwards and forwards any number of elements too. You need not traverse the whole list. Okay, so I don't want to go through this. I'll wait for next time. But we're done here. Okay, here we go. Let me close this though. Here we go. I'm gonna sudo make install. I'm gonna see if our system call works. Okay, sudo update grub. Whew, moment of truth. Okay, we're gonna sudo redo. Okay, that was fast. Hit that. And we don't have any of our logging anymore. I got rid of that stuff. So it's... Uh-oh. Wait. Oh, okay. Okay, so now what we need to do is compile our user space program called main.c here. Again, this, oops, I don't know what I just did. Okay, again, just open up gedit. That's our source code, super simple. We want to open up terminal, and then let's actually open up another terminal too to look at the message. So right now, nothing. Okay. So if we were to go to the desktop and gcc main.c, compiles nicely, just like a regular program. lsla shows us a.out, and then we just execute a.out, and result of the system call is 6 because we provided 4 and 2 and 4. And let's see what the message has. Did we log anything? Let's see. Nope, nothing. Okay. That's fine. I don't know if I... how about this? Was it grep average dev? Nothing? Weird. Huh. Oh well. Did I do current info? I don't even want to like recompile that, but we know it works, right? So current. Oh, I had a comma here. Ah, silly me. Okay, that's fine. That's okay. This was supposed to print. Let me just change that, and then I'll recompile, and then next time I'll show you. So if I did this, sys.c. Okay. This, oops, this is not supposed to be there, and But then you get the gist, right? Like, so now if I were to then change this to, I don't know, 2000. Oops, not dim. Compile. I see 2004, and this was supposed to show me something, but it's okay. We get the gist. So I'm gonna just make J24 again, and I'll just call it a day. See you next time.